Hello everyone, this is Bill, and I haven't recorded videos like this for a long time. And today I'm going to talk about dynamic programming. So why I'm going to choose it because it has a strong connection with reinforcement learning, which is one of the my research topics. So I would like to dive into dynamic programming. I also want to offer some easy understanding how you're gonna take it, care of this problem. So before we start, we can think about an interesting example. Suppose we run a small store and only accepts cash payments. In your cash drawer, you only have the coins of 11, 5, and 1 cents. So even the customer needs 15 cents in change. So how can you combine these coins to give a correct number using the fewest number of coins? So this isn't happening in our real world, right? So you can just imagine this in a magic world or a parallel world. So could this problem be solved by greedy algorithm? Let's have a think. Actually, it can give you a solution, right? In our real life, we just, um, for example, I can give a definition of the greedy algorithm. Like in the real life, if we have like 20, we have 10, we have 5, we have 2, and we have 1. And if a customer needs 15 cents, we just find the largest to can fit into it, right? Like 10 cents. We find 10 cents, and then we start to find 5 cents. Then it's gonna be two nodes to solve the problem. But here it can give you some solution, but is it the optimal solution, right? Like we can choose 11, the largest one can fit into it, and then we have the remaining four. It needs another four nodes, which in total 5 nodes. Is it the correct, the optimal one? Actually not. You can find smaller, number of coins to fit into it, right? Just the three of the five. So do we have a better option to solve it? Actually, yes, right. With dynamic programming, we can short for DP. So the key point of dynamic programming DP is divide the problem into subproblems. For example, if you currently have 15, you can choose 11, then remaining number would be 15 minus 11 before. So now you don't worry about 11, you don't worry about 15 coins, you start worry about 4, right? If the current number is 15 and you choose 5, the remaining number would be 15 minus 5 equals to 10. Then you start to think about 10. So in this subproblem case, it's much easier for us to solve, right? Like 4, we only have 11, 5, and 1. We cannot fit into 11 and 5. We can only fit into 1. Then it needs another 4 coins. But for 10, it's easier, right? It's 5 cents. We need just 2 coins to solve the problem. Then it will transfer an easier problem, a solved problem that we can solve, right? So this is what I put here, right? We change it into so we actually can design a function to depict the pattern. The Fn represents the least coins are required for money n. So our goal is the final goal is F15. So I put the prime here, meaning it's not the optimal position. I put it as a option here. So the F prime 15 equals to 5 because the F4, as I mentioned, we have 4. And F15, F1 minus plus 1. This 1 is the choice of current state. And it's gonna be, 2 plus 1 gonna be 3. So as we already discussed, the second one is the best option. If we choose 5, then we just choose the 3 times, then equals to the best one. And actually, we can build up a array contains each number of coins gonna be find with f function. Um, Start from F1 to F15, we can get this, we can say a checkbook that we can build later on with the program. I will show you. So now we can draw a conclusion. Fn is only related to the sub problem, sub options like 11, 5, and 1. Actually, we can write a formula formally here. it is the mean of this three options plus the one here. Actually, there is a more formal name for it. Is dynamic transition is a state transition function. So let's move into like key concepts in dynamic programming DP. Like first one is a state. Again, to talk about a state is a numerical description of a specific situation corresponding to the value of the problem in that situation. So how do we understand that? For example, this airplane chess, right? We have four players. So we have four turns, let's say, and each of player have four planes. Then we have in total 16 planes to move. So basically, we can use the turn like which player is in charge. Like for example, you are in charge, and the position meaning we have 16 planes to move, and each of the plane has 81 like step it can put, right? So in the end, we have this 17 numbers to depict the current, I can say, state. This current state I will show you is not a real state. It's just showing the current situation. So I put a prime here. Like for example, which player is in charge and a 16 playing how it goes, right? Actually, we should associate with the number. For example, the winning chance, then it become a state. Otherwise, it's just a situation. Now, if we associate with a winning chance, for example, your turn, and here is like 16 um, planes where it is, and then you associate how big your winning chance is. So this is how it works for state. So state transition from one state to another under a constraint of a problem. So we need a constraint accompanied by a change in value. So we have a state to another state, we have changes, and we should keep some promise and keep some rules. And how to make the best decision when having the whole picture. For example, in here, we just move the roll the dice for each of the plane to move. For example, it's your turn, you choose roll the dice, and you got a really good number like 6 for a plane, and then you move it, the farthest you can. So it will gain your winning chance. It's from one state to another, and you will accompanied by a value change. But this is kind of like the airplane chess is kind of like winning by luck, right? There are a lot of like chesses. For example, the real chess or the Go game, you need a lot of not of tactics or strategies to win the game. So you should count your move. And the third concept is down backtracking, no after effect. Once the earlier part of the optimal decision sequence has been determined, it cannot be revised because of the changes in the later decisions. For example, like our first example like finding the coins. If you decide F 10, it fixed. It won't be changed by any other like 15, right? If we put it into the scenario of machine learning and reinforcement, it's going to be Markov property. So you only affect the things in the future, you want to affect things in the past because past has been fixed. What you did is only influence the outcome of the future. Another example only shown in a DP is Fibonacci sequence. So let's imagine this sequence, each of the game. So the naive problem is 0 and 1. We start with 0 and 1. And each number behind is the summation of the first number, first two number, prior to number. Like 2 is the summation of 1 plus 1, and 8 is summation of 3 plus 2 plus 5. And so on and so forth. We can draw it here is this has the same the shape of the shell like we have here, and actually it has a very strong connection with the nature. There are a lot of like you can find a lot of objects in our real life like have coincidence with Fibonacci sequence, even like the arms of galaxy. So it's a very interesting sequence. Let's see how connected with DP. Actually, if we go back to the Fibonacci sequence, each of the number except the first two number is the summation of the prior two numbers, right? So we can write a solution here. For example, F5, you want to find F5, you have to find F4 and F3. If you want to F4, you have to find F3 and F2. So we can write a stack. It calls stacking technique in programming. So we write a function here, right? And except the naive problem, a naive solution, we will return, the subproblems. So imagine if you're trying to find F5, your all the way goes down to n equals to 0 and equals to 1. And the problem and the function is going to be backtracking to F5. But is it the optimum solution? Actually not, right? If, for example, like you can find this F3 has been calculated twice and F2 and has been calculated three times. It can waste a lot of time. If we can find a way to store these numbers, we can solve a lot of problem and speed up a lot. And actually, this has been solved in our previous problem, right? Not solved, but I can show you the solution later on. For the first example, we stored F1 all the way to F10, even F11, and then we can backtrack how the F15 for the coins finding problem. So the last one is the example I want to show is the Bellman-Ford algorithms. So Bellman-Ford algorithm is algorithm that computes the shortest path from a single source vertex to all the other vertices in a weighted diagram. So you can see we have 5 points, and 0 is the source point, and there is numbers on site, meaning the edge weight or their like default distance from one point to another. But actually, there's some negative ones. So in a real life, there can be networking sort of thing, right? So compared to this Dijkstra algorithm, Dijkstra algorithm actually a greedy-based algorithm. So it cannot deal with those negative edge weights. For Dijkstra algorithm, for each of the iteration, you're going to fix one point as the shortest path. And then you cannot be, post-processing if you consider this negative path weights. So it cannot be modified later on. But for a Bellman-Ford algorithm, it builds on DP. It can be modified. I will show you how. So Bellman-Ford algorithm has been proposed by two scientists, Richard Bellman and Lester Ford. And Richard Bellman is one of the big names in reinforcement learning. So it also shows, there's big connections with DP and reinforcement learning. So let's start with a concrete example. We still take this example, and we show two numbers on each of the points. The first point is it shows the predecessor of the problem of the shortest path, and the second number shows the shortest path currently. We initialize with all infinite, and you can see there's a 1, 2, 3, 4, 5, 6 here, meaning the iteration of each edge to be traversed is not fixed. You can try it randomly. It will affect the convergence speed, but you won't affect the final solution. So let's start with the first point. It's the first one to traverse, right? So the shortest distance is currently infinite, which is not ideal, but there's a 19 here. We can modify it into 90. And for the second one, there's no direct path here, so we ignore it. And sorry, for the second one is this, right? Is a positive infinite, and then we have 80 here. We modify it into 80. And for the fourth point is the third one to traverse is a 75. We modified it, and later on it's going to be interesting if we look at the fourth one. Is a 90 minus 30 is going to be 60. 60 is much smaller than infinite. Then we're going to be modifying to 60, and then we change the predecessor to 1 because it came from 1, right? So the same thing for the fifth, we have 60 and 1, and 70 is smaller than 75, we're gonna do change into 70. And later on, we have 6, 80 minus 30 are gonna be 50, and we modify into 50, and we'll change the predecessors. So on so forth, we will fix the second round. After the second round change, the solution's been fixed. So the third round won't change anything, then algorithm will be ended. And we'll finally give this solution from the source point to all the other points. And we can track the predecessors of each destination point easily. So this is a good sign. So for a Bellman-Fold algorithm, we can formally write down it here. We initialized with vertex vs, here, and initialize the distance to all the other points into infinite. And then we traverse, actually we loop over different edges, called a relaxation operation. So we'll compare the current distance of that point plus, the predecessor distance to that point, and plus the weight of that edge compared to current distance to that point. If it's smaller than that, we update it. We also updated the predecessor point, and we iterated. N is the total number of points. So we'll loop over n minus 1 times. It will guarantee the model will find the shortest path unless there is a negative cycle detection. There's a negative cycles, meaning if you loop over a sub loop inside of the whole graph, they will continually reduce the the distance, which is not reasonable, right? If you find a negative loop cycle, it will loop over and over again. It will reduce the distance of a certain type, a certain vertex, which is not reasonable. So except this, n minus 1 times will guarantee the solution. So for time complexity, the number of iterations will be v minus 1, and edge checked per iteration will be e, and so the overall complexity will be O, the big O VE. So before we jump at that, let's think about the Bellman-Fold algorithm. So I was thinking why the Bellman-Fold algorithm just use the v minus 1 iterations can guarantee it can be solved, right? If there is no negative cycle for sure. Why? Because I have to think about that. Why I found a solution. Because for the first iteration, it will modify, no matter how, no matter what is the order for different edges to traverse. Actually, it can guarantee the hope equals to 1 of the points will be updated. For example, like this, 1 will be updated. All right, this 3 will be updated and 4 will be updated, no matter the order, how the order is. But the second round, actually you can guarantee the second hope. For example, like this, the 2 is the predecessor of with a 1 here, right? You can update it for sure. Yeah, it can be updated like even further with by passing 3, right? But this is how it works. So guaranteeing. So in one of the distance, the chain of it, the biggest number of nodes, the biggest number of nodes gonna be the biggest number of edges gonna be v minus 1. So at least v minus 1 iterations can solve the problem if there's no negative cycle. So that's why it can work. It's a pretty smart algorithm because it's based on previous stored numbers. That's how DP works, right? You store your subproblem solutions and you're guaranteeing your subproblem solution is the optimal one, and your biggest one is based on that. You will build safely based on you're already guaranteeing the optimal one, and you will build up on that. You will solve the problem with the optimal solution. That's how it works. So the warning of programming, let's see. I wrote it down with C++. So this is one of the programming language I've used before. But it's on this algorithm is quite similar with Python. So we initialize with the current number with 15, and this f0, which is naive case, we f we assign it 0 to it. So we loop over from 1 to 15. We will check three options. We will choose the current cost, which is the very high number initialized, and we will choose the current cost with the other three options. Which one is the best one to choose? So I'll show you. Um, so I'll show you it in this online editor or online compiler. If you run it, you're gonna solve it with a couple of seconds, and it will show from the very beginning because we loop over from 1 to 15, so we can give this array which we maintain here. So F16, we maintain a 16 number here from F0 all the way to F15. We'll give that. So the idea is we solve it by bolting up the problem by solving the naive one, and we build up on that because naive one is guaranteed to be the optimum, and then we build on that to build the optimum one, and we stack layer by layer. So for the Bellman-Fold algorithm, we will maintain a array here, which is the source and target, and this is the distance from initial edge weights. And we also maintain this D and this P. D means distance, and P is predecessor here. So we'll maintain the distance of the thing. So for example, like 0 to 1, 19 is smaller than infinite. We're going to change it to 90. And we were going to change it to 3 to 80, 4 to 75. We also will check this 1 and 2 minus 30, and we have the 0 and 1, 90. We're going to make this 90 minus 30 to get 60 for the second one. 60 is smaller than the infinite. Then we will change the 60 here, as we showed it before, right? We'll also change the predecessors. So after two runs, actually the algorithm becomes stable. The results become stable, which is converged, and then you will get the final solution here. So we can have a look at the Bellman-Fold algorithm in Python. So we'll have the S, T, and W, just weights, and then we will loop over different edges. And this is a relaxation problem, relaxation operations. And we will have the source, target, and the weights here. We will check if the distance of the U, which is the distance from the source point to, I mean the 0 point to the source point here, plus to the predecessor, I mean, smaller than this V, then we're going to change it. And there's a negative cycle. Is if we jump out of the routes, it still can be optimized, meaning must be something wrong side, which is a negative cycle. So it all says negative cycle detected, and it will rebuild the path by backtracking all the points. So that's how it works. So is there a connection with reinforcement and DP? Yes, there are strong connections. So I just asked GPT for it, and I paste it here. So in classical dynamic programming like shortest path or knapsack, the recursive relation looks like this, right? The current reward, I can say, or cost or weights plus the previous one. So that's exactly what we saw in the Bellman-Fold algorithm to get the current one, right? It also how it works for reinforcement in the Bellman equation, right? So the current state value, which ensures how good the current state is for a certain type of pi. So we should have policy here, and is the expectation of A has been marginalized, and this S is also sampled from from the future state, this V pi S prime, by adding this reward. For the optimum policy, we have the Bellman optimal equation here, so which has been used for value function iteration in Q-learning, right? So they are basically, if you compare it with it, it has the same solution, same format, and actually based on the same idea of we decomposite the big problem into smaller problems, and we ensure the small problems. For example, the reward to the future has this maximum reward, then we can safely build on that the current state solutions. So this is the connection with reinforcement learning. And the message to be packed up, to be wrapped. So we had interesting examples. We talked about greedy algorithms. We talked about DP solutions we compare to, and the key concepts in dynamic programming: the state transitions, non-backtracking properties, and two algorithms: Fibonacci sequence and Bellman-Fold equation, Bellman-Fold algorithms. We also talked about programming and the connections with reinforcement learning. So that's how it work. How we learned today. Hope this would be very helpful, and thank you.